Okay, it's September 30th, 2016, and this is Steve Austin, a man barely alive that says no jive, also known as Jump Rooster, Heel Out Daughter, that's going to do a simple experiment that I learned in second grade for subtractum. Okay, this is going to demonstrate why objects that are actually over the horizon, according to a globe theory of the Earth, can be seen. And it has to do with a well-known principle called the refraction of light. Light bends as it passes through certain mediums, including air sitting on water. It'll bend generally along the curvature of the Earth. And so we're going to do an experiment. So we have a mark in the bottom there and a penny. The penny is going to act like our ship over the horizon. Now I'm going to put this penny so it's just touching this black mark. So it's about halfway touching the black mark. I don't know if you can see that there. Okay. And then I'm going to set it down in the cup. And you can just see it so that the camera's stable on a tripod. And I'm going to move the penny until it is just off the horizon. All right, see, there it is. It's off. You can see it. All right, so the penny is over the horizon. Camera's stable. Penny's stable. Have to be careful to pour the water in very slowly, not to disturb the position of the penny. Because otherwise you pour it too fast and move, but that's why I put the mark so you can see that it hadn't moved. So now I just got some water here. I'm gonna pour some water in this cup. Okay. Slowly at first. And our over the horizon penny, as the light reflecting off the penny passes through water instead of air, the light is refracted through the water at a different rate. And this principle of light refraction, no matter what light passes through, it refracts, which is why you can see things over a distance of 10, 15 miles, because actually the light is bending to follow the curvature of the Earth. Now, I'm not going to touch the cups at all. When the experiment's over, I'll show you that the penny hasn't moved. It's still on the mark. But we're almost full. We'll go full to get the full effect. There, it's full. So obviously, the penny, which was over the horizon, can now be seen. Why? Because the light is bending. Light is not going on a straight line from that penny to this lens. It's actually bending through the water so you can see it. Even though without the water, it's over the horizon. Now we're going to take a tube here. Because I saw this experiment. I did this in second grade, and I also saw it on YouTube. That's what reminded me of it. But I'm going to do one better than the YouTube one, because I am now, without touching and moving the cup, I'm going to siphon the water out. So we saw the ship appear beyond the horizon. And now we're going to see it disappear over the horizon. Haven't moved the camera, haven't moved the cup. So I'm going to put this tube in here, suck it a little bit to get the siphon going. Fortunately, we have a sink right next door, so that siphon's going. You can see it starting to drain. Move this out of the way. Keep your eye on the penny. As the siphon drains the water, the penny slowly starts to disappear over the erstwhile euphemistic hypothetical horizon, which is the edge of this cup. Still siphoning out. Still siphoning. Fortunately, I have a sink right next to the cup. Okay. Well, there's a little bit of water left, so you can see the edge of the penny. But there we saw the penny that hasn't moved with respect to the line of sight of this lens. But you could see it when the light was passing through the water, and then you couldn't see it when the light wasn't passing through the water because of a well-known principle called refraction of light passing through air or water. Water's better because it's denser and you can see the effect short. So now I'm gonna add some water back, and so it disappeared, it appeared. You couldn't see it, then it appeared, then it disappeared, except for that little bit because there's a little bit of water. I couldn't get the siphon all the way down. Now it's gonna reappear. We're gonna fill it back up. And there it is, our over-the-horizon penny in plain view, even though it is truly over the horizon. The light is bending around the curve, the lip of that cup, so you can see it in the lens. And just for one more time, for kick's sake, I'll siphon it, and then without moving the cup, I'll then move the camera for the first time and show that the edge of the penny is still about halfway covering the black mark in the bottom. So start the siphon. Maybe if I get this tube a little bit further down in the cup, I can suck it out more completely. It's kind of tricky because I don't want to touch the cup, certainly, because that would be one way to say, aha, he moved the cup, that's why. I should have put a mark on the counter, but I didn't think my wife would appreciate me marking the counter with the Sharpie. But as you can see, as we drain the water, penny hasn't moved with relation to the camera lens, but the penny's disappearing because the light is not refracting as much. And again, this simple second grade experiment shows why when people get their little curvature of the earth calculators and they go out and they measure some distance and then they look at something and they say, well, I can still see it, the earth must be flat. No, they just don't understand science, principles of light, and simple properties such as refraction. If they calculated for refraction, they would understand this. And so now, I haven't moved the cup. I'm going to move the camera for the first time and show that the penny is in the same, shoot, this camera's got like a spot right there. Right where we started, halfway across the black. But anyway, that's why you can see things, 15 miles across Utah Lake that should be quote unquote over the horizon. They really are, but they look like they're not because the light's bending and refracting just like the penny.